Hello everyone, welcome back. In the previous video, we discussed recurrent neural networks or RNNs and the different types of RNN architectures. RNNs, as we discussed, are designed specifically to handle sequence data, whether it's text, language, speech, time series, anything where the order of the data matters. And we learned that one of the key strengths of RNNs is their ability to carry information from one step of a sequence to the next. In other words, they have a notion of memory. But see, something interesting happens when the sequence becomes very long. For example, as in human language, RNNs start struggling. They begin to forget earlier parts of the sequence, and sometimes the network itself becomes very difficult to train. So the natural question is, why does this happen? Well, in this video, we will look at all these challenges that RNNs face, particularly when dealing with long sequences. In particular, we'll understand two key issues, the memory limitations and the unstable gradients problem. And once we understand these problems, the motivation or need for more advanced networks like LSTM or GRU will become very clear. All right, let's jump into the video. In this video, we're going to talk about sequences that are very, very long and the issues that might come because of long sequences. So what do I mean by long sequence? For example, if you see this is a customer review for a product, they bought. And to understand, let's say we want to do a sentiment analysis on these customer reviews to see if it was negative or positive. And let's say RNN was reading this sequence. See, just reading the initial portions of the sequence, it won't be clear. For example, as you can see here, I brought this product last month and initially I was really excited. Looks positive, right? And then the package was great and the product looked exactly like the pictures online. So far, so good. But however, after using it for a couple of weeks, I started noticing some issues. The performance wasn't as good as I expected and it kept freezing during the use. I contacted customer service and while they were friendly, they did not offer a solution. So this particular phrase is kind of ambiguous here. Over time, the problems just got worse and now I regret purchasing it. And I wouldn't recommend this to anyone. So if you see, to understand that this review is indeed negative, right, one has to read the entire sequence. So if an RNN is looking at this sequence, right, it cannot, make up that it was a positive review or negative review just by looking at the earlier parts of the sequence. It has to read the entire sequence. Now, this is a problem with RNNs, especially with respect to the memory, in dealing with long sequences. So now you may ask, wait a minute. We thought that memory is a strong point with RNNs compared to the dense layers and CNN layers we talked about in the previous sections, right? That is correct. See, for example, if you see RNN, right, compared to the dense layers and CNN where they did not have a concept of memory, there is a concept of memory in RNNs, especially as you can see in this architecture, right, which we discussed in the previous video. At each time step, the activation is fed into the subsequent time step. So there is a memory. So each time step, in a way, is dependent on its previous time step. But see, these dependencies work only for short-term dependencies. If you have very long sequences, RNNs will have a problem with the memory. So this is one of the problems with long sequences and using RNNs for dealing with long sequences, the memory issues. While these RNNs are compatible, they work well for sequences that are relatively short. If you're talking about very long sequences, what happens is as you go towards the end of the sequence, the RNNs will forget what they have learned in the initial portions of the sequence. Okay, so that's the one big problem in using RNNs for long sequences. Another problem is that, again, when you're dealing with long sequences and if you're using RNNs, the RNNs have to become very deep. Like, for example, the architecture which we see here, this has 30 time steps. But the customer review we're seeing here, it has almost like 80 tokens, right? 80 time steps. And there could be sequences much longer. And then the RNN becomes even more deeper. So having RNNs that are very, very deep can result in some other issues called unstable gradients. So the gradients can become unstable. because we need the gradients to update the weights and train the model, right? And these gradients can become unstable with the result that it may take a long time to train or simply not train at all. Okay, so why would that happen? Well, because of two issues related to gradients, unstable gradients. You could have vanishing gradients and you could also have exploding gradients. See, these kinds of unstable gradients, they're also an issue with, like, the image, the computer vision problems we have dealt with in the previous section, right? When we're dealing using dense layers or deep networks. So when we're dealing with images and CNNs or dense layers, right, there we talked about these vanishing gradients in particularly. That we said that all these layers in a deep network are chaining on top of each other. And when you chain all these things, right, the gradients, simply again, if they are very small and if you are multiplying small things, when you multiply many small things with each other, they become even more smaller and the gradients can simply vanish. Right? So we talked about this for the images when dealing with deep networks of dense layers of CNNs. Well, the same issue arises here also. Now you may say, wait a minute, like all we see is a simple RNN layer, single RNN layer, right? We don't have a deep stack. So maybe the issues happen only with deep stack of RNN layers? Well, not necessarily. Even a single RNN layer, if the sequence is very long, can present us with these unstable gradients problem. So why is that? So again, if you look at a single RNN layer, right, each time step is stacked with the previous time step, right? So remember the equations which we use to compute these activation functions, A1. So we use A1 and X2 to compute A2, A2 and X3 to compute A3, A3 and X4 to compute A4 and so on. So in a way, each time step is chained or stacked on top of each other. Right? So the same problem which we saw with the images, or when you had a deep network, you will have the same problem when the sequences are long. So especially when you're calculating, for example, the loss function, right? And you want to take the gradient of this loss and use that to update the weights, right? So when you take the gradient of this loss function, how do you calculate the gradient of the loss function? So in the back propagation, right, you have to use like this chaining. So in a way, you're essentially calculating the derivatives of, each of this activation at each time step. And when you are calculating all these gradients, and if all these gradients are smaller, right, you're multiplying many smaller quantities, the result will be even more smaller. And you end up with not updating the weights at all. If you don't update the weights, basically you're not training at all. So this is the vanishing gradients problem. But you can also have exploding gradients. So now you may say, how is that? We can have both vanishing and also exploding? Yes, the same thing works the other way, right? Again, you're chaining all these gradients, you're multiplying all these gradients together. If the gradients are very small, you multiply very small gradients, you will have vanishing gradients. Similarly, if the gradients are very big, you're multiplying very big quantities with each other, and you could have even bigger gradient and basically exploding gradient. Both are not good, okay? So these are some of the issues when dealing with long sequences. So how do we handle it? What are the techniques to deal with these unstable gradients? So let's talk about the unstable gradients problem first, then let's talk about the memory issues, what we're going to do with the memory issues. So how do you deal with unstable gradients? Well, the general tricks and techniques that worked for, in general, deep networks or in deep learning can also be used here. What are they? Good parameters or weights initialization. Initialize these weights in a smaller way, right? And then, fast optimizers can help. Regularization techniques like dropout can help. So all these things can help. These are generally the best practices. And these can also help to some extent with this unstable gradients issue. But more clearly, if you're dealing with exploding gradients, you can monitor them. And you can clip the gradients. There's a technique called gradient clipping. You can use that. Or just like we described earlier, better weight initialization will help with the exploding gradients as well. And also the learning rate. If you use a smaller learning rates, that can also help with the exploding gradients. What about the vanishing gradients? Well, for vanishing gradients, particularly the layer normalization can help. Remember the normalization? But see, the normalization that we talked when we dealt with images in computer vision, we talked about something called batch normalization, right? When we talked about batch normalization with images and CNNs or dense layers, right? There, the batch normalization was we're normalizing the data in each batch with the mean and frequency for that particular batch. Now, layer normalization is different than batch normalization. Let me explain how we implement layer normalization in an RNN layer. So for example, if you see this RNN architecture with multiple units, in a single RNN layer, layer normalization means we're going to normalize the output of the hidden state at each time step. So we compute the mean and variance, right, of this RNN layer at each time step. And we use that to normalize the output of the hidden state. And then we feed it into the next and subsequent time steps. It has been observed that implementing layer normalization can be a better help in dealing with unstable gradients, particularly vanishing gradients. So when you normalize the data in this fashion, it has been observed that it can stabilize the gradients to some extent from shrinking too much and can contribute to helping with the vanishing gradients. This can also indirectly help to some extent with the exploding gradients also, but mostly for exploding gradients, gradient clipping is primarily helpful, and also better weight initialization. Okay. And coming back to the vanishing gradients, instead of regular RNNs, we can also use something called more specialized networks called LSTM and GRU. LSTM stands for long short-term memory, and GRU stands for gated recurrent unit. We're going to learn about these networks, in the next few slides. All right. So this is what you do in dealing with the vanishing gradients. Now, apart from the gradients, the outputs themselves can become larger. Why will this happen? Well, especially if we use some kind of a non-saturating activation functions like ReLU, it could result in output becoming very large. But typically for this situation, tanh function is generally preferred and is the default in an RNN layer. In fact, as I said earlier, when we implement an RNN layer, by default, it uses a tanh function. Okay, and smaller learning rates can also help with this problem. Okay, so these are some of the techniques that we can use in dealing with unstable gradients. So what about the techniques to deal with memory issues? Let's take a look. Again, as sequences become longer, simple RNNs have trouble remembering the earlier portions of a very long sequence. So what is the solution? Well, we can use a variation of RNNs called long short-term memory and gated recurrent unit, LSTM and GRU. So both these think of them as a variation of RNN, except that they are more involved and have a little bit more complexities. And they do that so that, they can help in remembering these long-term dependencies. They allow past information, both these networks, they allow past information, right, to be re-injected at a later time, and thus helping with this memory issue. They can also help with faster convergence. Okay, so how exactly do LSTM and GRU address this memory problem when dealing with long sequences? And what do these architectures actually look like? Are they similar to RNNs, or are they very different? And if so, how different? Well, to understand all of that, please stay tuned for the next video where we will look at LSTM and GRU architectures in more detail. These networks work again much better for long sequences, and in fact, these were the architectures on which some of the first generation language models were built until transformers and later ChatGPT came along and kind of spoiled the party. Or maybe I should say completely enhanced the game in AI. But first things first, in the next video, we'll understand LSTM and GRU in detail, and that will naturally pave the way for understanding one of the amazing discoveries in modern AI, and that's transformers, and that's for later videos. Okay, so see you in the next video, and as always, happy learning.